Hello students, in today's lecture we are going to learn about gravitation NCERT section 7.8 and we will also solve an example 7.4. This is disclaimer. Learning objectives. By the end of this lecture you will able to understand the concept of escape speed. So in today's lecture we will cover first 7.8 escape speed. Then we will solve an example 7.4. So escape speed. Let's start by considering what happens when we throw an object upwards in upward direction. Notice how it reaches a maximum height through maximum height before it falls back to earth. This is due to the gravitational pull of the earth, which slows the object down until it stops momentarily at its peak height. Now if we increase the initial speed of the object, it will reach a greater maximum height. Alright, and this is because the object has more kinetic energy to overcome the gravitational pull, and that allowing it to travel further upwards before gravity brings it back down. Is there an initial speed that would allow the object to escape Earth's gravity completely and never return? This introduces the concept of escape speed, which is important in understanding how objects can leave a planet's gravitational field. So answer is yes. There is such a speed and it's known as the escape speed. This is the minimum speed needed for an object to break free from Earth's gravitational pull without any additional propulsion. It's a key concept in space travel and exploration. So let's talk about definition. So basically, escape speed is defined as the minimum speed with which a body must be projected from the surface of a planet so that it escapes the gravitational field of the planet and never returns. This means that if an object reaches this speed, means escape speed, it will continue moving away from the planets indefinitely. Alright. So achieving the escape speed ensures that the object will never return to Earth. And this is why rockets need to reach a certain speed to leave Earth's atmosphere and enter space. Alright, and understanding escape speed helps us grasp the challenges of launching spacecraft. Now we will diving into the mathematical analysis of escape speed. This is a important concept in physics that helps us understand how an object can break free from Earth's gravitational pull. We will explore the energy dynamics involved in this process. So let's start by considering an object that thrown with an initial speed, and that is denoted as vi, from a distance of h plus re from the center of the earth. Here re represents the earth's radius and h is the height over the earth's surface. So total initial energy of the object, which is the sum of its kinetic and potential energy. So the equation is E of h plus re is equal to half mvi square minus gme into m divided by h plus re plus u1. In this equation, small m is the object's mass, capital G is the gravitational constant, and capital ME is the Earth's mass, and the U1 is a constant representing potential energy at infinity. Alright, and this equation helps us quantify the energy at the starting point. So suppose what happens when the object reaches infinity. So at this point, it means at infinity, it has a final speed Vf. Alright, and this scenario allow us to analyze the energy state when the object is far from Earth's gravitational influence. So at infinity, alright, the total energy is given by E of infinity is equal to U1 plus mvf square divided by 2. This equation shows that the potential energy at infinity and the kinetic energy at this point determine the total energy. And understanding this helps us see how energy conservation plays a role in the escape speed. And it's important to note that U1 denotes or we can say represents the gravitational potential energy of the object at infinity. This concept is important because it sets the reference point for potential energy when the object is no longer influenced by the Earth's gravity. So let's continue with mathematical analysis of escape speed. The principle of energy conservation. So here the total initial energy of an object is equal to its total final energy, and the expression is mvi square by 2 minus gme into m divided by h plus re plus u1 is equal to u1 plus mvf square by 2. So notice how the kinetic energy and gravitational potential energy terms are balanced. This equation is important for understanding how energy is conserved as an object moves away from Earth. Now consider the case where the object just reaches infinity, meaning it has just enough energy to escape Earth's gravity. In this scenario, the final velocity Vf is 0. This simplifies our equation to mvi square by 2 is equal to gme m divided by h plus re. And this tells us that the initial kinetic energy must equal to the gravitational potential energy at the starting point for the object to escape. In this final step, we identify Vi as the minimum speed required for an object to escape Earth's gravitational pull. Now, known as the escape speed as a. All right. So the formula for escape speed is Vi is equal to V escape is equal to under root 2 into Gme divided by H plus Re. And this equation shows us that the escape speed depends on gravitational constant G, the mass of Earth me, and the distance from the center of Earth, that is H plus Re. Alright. Let's continue with mathematical analysis of escape speed. So, escape speed from Earth's surface where the height is h is 0. Alright. The formula for escape speed is V escape is equal to square root 2 into Gme divided by Re. Here G is the gravitational constant, m is the mass of the earth, and Re is the radius of earth. This equation is important for understanding how much energy is needed to leave Earth's gravitational influence. Next, we will rearranging the formula using the expression for gravity. So, G is equal to Gme divided by Re square. Alright. So, by substituting this into our escape speed formula, we get V escape, that is equal to under root 2Gre. This shows us how escape speed is directly related to Earth's gravity and radius, making it easier to calculate using known values. So now let's substitute the actual value for Earth's gravity and radius into our formula. So with the value of g, small g, that is 9.8 meter per second square, and radius of Earth, that is 6.37 into 10 raised to the power 6 meter. So we calculate escape speed, that is under root 2 into 9.8 into 6.37 into 10 raised to the power 6. This results in an escape speed of 11.2 kilometer per second. Alright. Therefore, the minimum speed as an object have to leave the planet Earth is 11.2 kilometer per second. This is a critical concept in physics and space exploration as it determines the energy needed for spacecraft to enter orbit or travel to other celestial bodies. Now, we are going to calculate the escape speed for the moon. So first, we have the radius of moon, which is 1.74 into 10 raised to the power 6 meters. Next, we have the gravitational acceleration on the moon, which is 1.6 meter per second square. This is much less than Earth's gravity, which is why the moon's escape speed is lower. Now, let's look at the formula for escape speed. The escape speed is calculated using the formula V escape is equal to under root 2gr. This formula shows us that escape speed depends on the both gravitational acceleration and radius of celestial body. So substituting the values, we have we calculate the escape speed for the moon as V escape is equal to under root 2 into 1.6 into 1.74 into 10 raised to the power 6. So solving this, you will be get the value, that is approximately 2.3 kilometer per second. Notice how we use the square root to find the speed. So escape speed of the moon is 2.3 kilometer per second. This means the object must travel at this speed to break free from the moon's gravitational influence. Gas molecules moving faster than 2.3 kilometers per second can escape the moon's gravitational pull. This is a key reason why the moon does not have an atmosphere like Earth does. So the moon lacks an atmosphere because its escape speed is low enough that gas molecules can easily escape into space. This highlights the relationship between the escape speed and atmospheric retention. Escape speeds for different celestial bodies. So the escape speed is the minimum speed needed for an object to the break free from the gravitational pull of a planet or star without further propulsion. For Mars, the escape speed is 5.0 km per second. This means that any object like a spacecraft must reach this speed to leave Mars' gravitational influence. The escape speed for Jupiter, so that is 59.5 meter per second. This is because Jupiter is much more massive than Mars, so it has a stronger gravitational pull. This is this higher escape speed reflects the greater energy required to overcome Jupiter's gravity. Now we will talk about the Sun. So the sun speed for the escape speed for the sun, which is a staggering 617.5 km per second. The sun's immense mass results in a very strong gravitational pull, requiring a significantly higher speed to escape its influence. So, students, now we are going to explore the energy perspective of space speed in the context of gravitation. This concept helps us understand how objects can escape the gravitational pull of a planet or star. Let's start by looking at objects with a speed greater than the escape speed. So, when an object has a total energy greater than 0, it means that the kinetic energy represented by 1 by 2 mv square minus uh, kinetic energy 1 by 2 mv square is greater than the gravitational potential energy represented by minus gmm divided by r, and this positive total energy indicates that the object can overcome gravitational attraction. So the equation of the total energy E is equal to half mv square minus gmm divided by r is greater than 0. Notice how objects with positive total energy follows hyperbolic trajectories. So this means that they have enough energy to escape the gravitational pull completely and will never return to central body. It's like a throwing a ball to so hard that it never comes back down. Now let's consider objects with negative total energy. It means E is less than 0. When E is less than 0, these objects follow elliptical orbits. This means they are gravitationally bound to the central body, much like how planets orbit the sun. They don't have enough energy to escape, so they remain in a stable orbit. These elliptical orbits are considered bound states. The object is gravitationally bound to the central body, meaning it will continue to orbit indefinitely unless acted upon by an external force. So next we have objects with a total energy equal to 0. It means E equal to 0. In this case, the objects follow a parabolic trajectory. This is the condition for just escaping the gravitational pull, where the object will reach an infinite distance with zero kinetic energy left. It's like a uh, throwing a ball just hard enough that it never comes back, but also does not keep going faster. This represents the condition for just escaping, meaning the object will reach an infinite distance with zero kinetic energy. Example 7.4. Two uniform solid spheres of equal radii r, but masses m and 4m have center to center separation 6r. A projectile of mass small m is projected from the surface of sphere of mass capital M directly towards the center of the second sphere. Obtain an expression for the minimum speed v of the projectile so that it reaches the surface of the second sphere. Alright, so we will solve this example. So let's see the solution. We have two spheres, both have the same radius. This is important because it simplifies our calculations by allowing us to focus on the mass and distance between these spheres. Alright, so masses are m and 4m, and center to center separation is 6r, and projectile is having mass m. So need to find minimum speed v to reach second sphere's surface. Alright, so the minimum speed of the projectile. This occurs when the projectile reaches a point where its kinetic energy is 0. At this point, all the initial kinetic energy has been converted into potential energy due to the gravitational pull of the spheres. Next, we identify point N, where the net gravitational force on the projectile is 0. This is the neutral point between the two spheres. Understanding this point is important because it marks the transition where the gravitational influence shifts from on one sphere to the other. Beyond point N, the projectile will be pulled by the gravity of the second sphere. This means that once the projectile passes this point, it will naturally be drawn towards the second sphere, highlighting the gravitational dominance of the larger sphere, larger mass. Now let defines R1, the distance from the center of the sphere with mass capital M to point N. This distance helps us to calculate the gravitational force acting on the projectile from the first mass. Similarly, R2 is the distance from the center of the sphere with mass 4m to the point capital N. By knowing both R1 and R2, we can better understand the balance of the forces at the neutral point. Alright, so the gravitational force is acting on the projectile at point N. The net gravitational force is 0. This means the gravitational pull from both spheres is balanced. So we express this balance with the equation gmm divided by r1 square is equal to g into 4m into m divided by r2 square. Here g is the gravitational constant, capital M is the mass of this capital M, and the 4 into capital M the masses of the sphere respectively. M is the small m is the mass of the projectile, and r1 and r2 are the distances from the centers of the spheres to the point N. So now let's simplify the equation. By dividing both sides by gm, we get 1 by r1 square is equal to 4 by r2 square. This equation shows the relationship between the distances r1 and r2, where the gravitational forces balance. Okay, so solving for r2 and r1. Here we have equation r2 square is equal to 4 times of r1. This equation shows that the square of the distance to the second sphere is 4 times the square of the distance to the first sphere. So from the previous equation, we can write r2 is equal to 2 times of r1. So total separation between the centers of these spheres is 6r. This equation allows us to find the individual distances r1 and r2 by substituting the relationship. Alright, so r1 plus r2 is equal to 6r. Now substituting r2 is equal to 2 times of r1 into the equation, so r1 plus 2r1 is equal to 6r. So r1 equal to 2r. This tells us the distance from the center of the first sphere to the point where the projectile is launched. Therefore, r2 is equal to 2 into 2r is equal to 4r. So the point N is located 2r from the mass m and 4r from the mass 4m. This positioning is critical because it affects the gravitational forces acting on the projectile. Alright. So let's continue with the solution. So let's start by considering the projectile's journey. It begins at the surface of the first sphere, and as it moves towards the second sphere, it reaches a point where its kinetic energy becomes zero. This point is important because it marks the transition where the projectile is solely influenced by the gravitational pull of the larger sphere. Beyond this point, the gravitational pull of the larger sphere, which is 4 times uh, more massive, becomes dominant. This greater pull is what will eventually allow the projectile to reach the surface of the second sphere. To solve this, we will apply the principle of conservation. We will compare the energy at the initial point where the projectile is launched and at the point where its kinetic energy is zero. This approach will help us to derive the expression for the minimum speed needed for the projectile to complete its journey. Alright, so initial potential energy of the projectile when it's on the surface of the gravity sphere with mass 4m, the potential energy is given by the formula PE is equal to minus gmm divided by r minus g into 4m into m divided by 6r minus r. Here g is the gravitational constant. So solving this, you will get PEI is equal to minus gmm divided by r minus 4gmm divided by 5r. This shows us the combined gravitational potential energy from both spheres acting on the projectile. It's important to see how the distance between centers of the spheres affect the potential energy calculation. Alright. So initial kinetic energy of the projectile, the formula for kinetic energy is KEI is equal to half mv square. And final kinetic energy at point n, final potential energy at point n is PEF is equal to minus gmm divided by r1 minus g into 4m into m divided by r2. So now let's look at the final potential energy of the system. The formula for potential energy between two masses is given by minus gmm divided by 2r minus 4 gmm divided by 4r. So solving this, you will be get PEF is equal to minus gmm divided by 2r minus gmm divided by r. Let's continue with the solution. So final potential energy of the system, the formula is given is PEF is equal to minus 3 gmm divided by 2r. Here g is the gravitational constant, m is the mass, and small m is the masses of the spheres of the projectile. Alright. So this equation shows us how the gravitational potential energy is calculated when the projectile reaches the surface of the second sphere. Alright, and the negative sign which indicates that the potential energy decreases as the projectile moves closer to the second sphere. So final kinetic energy at point n, minimum speed implies it just reaches n, so kef is equal to 0. Now according to conservation of energy, sum of kinetic energy plus potential energy is equal to final kinetic energy plus final potential energy. Or we can say initially the projectile has the kinetic energy and potential energy due to its position relative to two spheres. This equation we use kinetic energy initial plus potential energy initial is equal to kinetic energy final plus kinetic energy potential energy final. So now let's substitute the expressions for kinetic energy and potential energy into our expression. So it will be 1 by 2 mv square plus into minus gmm divided by r minus 4 gmm divided by 5r is equal to 0 plus minus 3 gmm divided by 2r. So solving this, you will be get 1 by 2 mv square is equal to gmm divided by r plus 4 gmm divided by 5r minus 3 gmm divided by 2r. Alright. So solving for v, so it will be 1 by 2 mv square is equal to gmm into 1 by r plus 4 divided by 5r minus 3 divided by 2r. So it will be 1 by 2 mv square is equal to gmm divided by r uh, into 1 plus 4 by 5 minus 3 by 2. So let's start solving for the minimum speed v. We use the conservation of energy here. So solving further, you will be get 1 by 2 mv square is equal to gmm divided by r into 10 plus 8 minus 15 divided by 10. So it will be 1 by 2 mv square is equal to gmm divided by r into 3 by 10. Alright. Now v square equal to 2 gm divided by r into 3 by 10. Solving further, you will be get v square equal to 3 gm divided by 5r. Now minimum speed v of the projectile so that it reaches the surface of the second sphere is v equal to under root 3 gm divided by 5r. So before we end today's lecture, let's quickly go through the summary of what we have learned. So escape speed, v escape is the minimum initial velocity needed for an object to overcome a planet's gravitational field. For the surface, for the Earth's surface, uh, v escape is equal to under root 2 gme divided by re is equal to under root 2 gre is equal to 11.2 kilometer per second. So for moon, its escape speed is only 2.3 kilometer per second. Now energy condition. For different trajectories, these conditions help us uh, understand how an object and energy affects its path when escaping a gravitational field. So E is greater than 0, hyperbolic trajectory, E equal to 0 parabolic trajectory or exact scape, and E is less than 0 elliptical orbit bound state. Other scape speeds, for Mars it is 5 km per second, for Jupiter 59.5 km per second, for Sun 617.5 km per second, and for any height h above the Earth's surface it will be under root 2 g me divided by h plus r. Alright, so at the end of the lecture we have some practice questions. These will not only help you revise today's concepts but also build your problem solving skills. And most importantly, solving these questions will help you a lot in your exam preparation. So first, why does not the moon have an atmosphere while Earth does? Second, what is the formula for escape speed from Earth's surface? What happens to an object thrown with exactly the escape velocity? What type of trajectory does an object follow if its total energy is positive? If a planet has twice the mass and same radius as Earth, how would its escape speed compared to Earth's? Alright, so these are the practice questions and these are homework for you. Thank you for your attention.